Anyway, we have a translational and a rotational velocity V and omega, and we have that stay constant in an interval delta t, or delta t capital, just to be coherent with the notation of the that I used. The velocity, the translational velocity only applies to the local x-axis of the robot. No? And, well, so said, we know that if I have a constant translational velocity and if I have a constant rotational velocity, I'm constrained to move along a circle. Okay? Constant translational velocity, I move at a constant motocircular uniform. No? Circular uniform motion, I don't know how you say it in physics. And I'm constrained to move along an arc of a circle, right? Let's say that the radius of this circle is, let's say here, and let's call it r, okay? We know that our platform will be moving on an arc of a circle. Of course, the circle will be lying on the y-axis. Let's say that this will be the motion of my robot. Okay? And this is the arc of the circle. Understood? I think so. So now, being the arc of the circle, we can, if we integrate the linear velocity over a time delta t, we could obtain a displacement, so the linear distance traveled by the robot in this time. And we can write, and we call this delta rho, which is equal to v times delta t. And if we do the same for the omega, which is the rotational velocity, and we integrate it over delta t, given that it's constant, we could call this quantity delta theta, which is equal to omega times delta t, t capital. Is it visible? Yes. Okay? And we have this relationship. We said that the robot moves of an arc r. Clearly, this change in orientation will be equal to delta theta. No? The change in orientation between this position and this position is change in angle. No? This change in orientation, when the robot rotates, moves along this arc, it will have a change in orientation, right? And this change in orientation will be our delta theta. Okay? Which is this angle over here, right? And which is equal to this angle over here by the identity of triangles. So we can say that this is delta theta. We can say that this part over here, this arc of a circle, which is the linear distance traveled by the robot, is delta rho. Understood? Okay, now I have the radius, I have an angle, and I have a linear displacement. So it's pretty straightforward to say that this arc of a circle is equal to the radius multiplied by the angle. And we can straightforwardly write that delta rho is equal to r times delta theta. Okay? Clear? Okay, so now, having said that, obviously you can recover rho from this, right? And you can recover r from this, and you can straightforwardly write that r is equal to delta rho over delta theta. And I'm gonna do it without deleting much code. Well, you have it in the document anyway. Okay? Now, remember that this is my origin, right? This is the origin of my reference frame. Okay? And then once the robot moves, basically, it will move, so it will describe me another reference frame. Okay? Now, how much is this rotation over here? It's clear. It's delta theta. Exactly. So the angle between this reference system and this reference system is obviously delta theta. Okay? How much is this displacement along, so this displacement here, along the x-axis? What I'm asking is, how much is this displacement between here and here? Basically, the displacement of this point along the x-axis. Sorry?
Times cosine of delta theta.
Cosine of delta theta? No, it's like if the delta theta would be 0, then the displacement would be 0, right? This is an arc of a circle. This is a circle. Assume that r is the unit, is 1, right? Like, how much is this elevation over here? It's the sinus of the angle, right? So, like, basically, I can call this quantity over here delta x, which is equal to r times sinus of delta theta. No? It's this quantity over here. How much is this quantity over here? Which we call delta y, right? Think about it, a little bit of geometry. If this was the origin, right? How much would be this interval over here? If this was the origin, this interval would be r times cosinus of theta, right? Because if theta would be 0, the cosinus would be 1. This interval over here. Now, how much is this? This is r, right? So, like, this segment over here is r, which multiplies 1 minus cosinus of delta theta. Clear? All right. However, okay, so and delta theta, I have it from here. So basically, I'm able to predict the location of how much my reference system, how much my system would move if it was starting from the origin and we applied to this system a constant rotational and translational velocity over a time interval. Alright? Now, if you want to implement these things, you have to be careful because there is a singularity. What happens when the robot moves like at 0 rotational velocity? Well, it happens that delta theta is equal to 0. If delta theta is equal to 0, r goes to infinity. And this is no nice, right? One could capture that case with an if statement. Because remember that we have also to implement these things. We don't have only to talk about them. this is kind of unnice. So like then there is the Grisetti trick, which is okay. Let's get rid of this singularity, like at least from the computational point of view, from the machine point of view. Also because we know that well, if I have finite rotational and translational velocities and finite time intervals, well, I cannot jump into the blue sky. So an infinity is not really like intrinsically present in the formulation. So what we could simply do is, in these two equations over here, replace, explode the definition of R, and use this expansion over here. Describe R as delta rho over delta theta. Huh? So I'm going to do it, you have it in the document, so I allow myself to overwrite the things on the blackboard, okay? Hopefully it's still visible. Instead of R, I will put this expansion over here. Okay? This was R before. And here I find something very, very interesting because I have a funky form which is sinus of theta over theta. And here I have another funky form which is 1 minus cosinus of theta over theta. Now, for sure you remember from school or from signal theory actually that sinus of theta over theta admits a finite limit for theta equals to 0, and this limit is equal to 1. And you might also remember that 1 minus cosinus of theta over theta admits a finite limit at theta equals to 0, which is equal to 0. Okay? However, there are higher order terms. What can we do? Like, remember also that in these systems, delta t, the integration interval, is typically very small because we are working with real-time systems that go in the order of 10 milliseconds, 5 milliseconds or so. And as a consequence, being delta theta small, theta is typically also relatively small, right? So what we can do is to replace these two formulas, these two equations here that I'm now going to rewrite only for sake of clarity. I'm going to rewrite just for clarity. We could replace these two formulas, which, as you see, they are just like functions of theta, by their Taylor expansion around delta theta equals to 0. Taylor expansion truncated to the order that we want.